For centuries, classical physics stood as one of humanity's greatest intellectual achievements. It was not merely a collection of formulas, but a worldview, a promise that nature could be fully understood through continuous laws, smooth curves, and deterministic equations. From the motion of planets to the vibration of strings, from the flow of heat to the propagation of light, everything appeared to obey principles that were elegant, predictive, and complete. By the late 19th century, many physicists believed the major work was finished. What remained, they thought, were only refinements, small corrections in decimal places. Yet beneath this confidence, a quiet and unsettling problem was taking shape, one that would expose a deep and fatal weakness in classical thinking. The problem emerged not from exotic cosmic phenomena or rare laboratory conditions, but from something astonishingly ordinary: heat. When objects are heated, they glow. A piece of iron pulled from a furnace glows red, then orange, then white as its temperature increases. This glow is not decorative. It carries precise information about the object's temperature and internal energy. Physicists sought to describe this glow mathematically, to predict how much energy an object emits at each wavelength of light when it is heated. The task seemed straightforward. After all, classical physics already possessed theories of electromagnetism, thermodynamics, and statistical mechanics. These tools had explained nearly everything else. Surely they could explain glowing objects as well. To make the problem clean and universal, physicists imagined an idealized object, a perfect absorber and emitter of radiation. This object, later called a blackbody, absorbs all incoming radiation, regardless of wavelength or angle, and emits radiation solely based on its temperature. It does not reflect or transmit energy. It absorbs and re-emits it entirely. Although no perfect blackbody exists in nature, physicists could approximate one using cavities with small holes. Radiation entering the hole would bounce around inside, gradually being absorbed by the walls. The radiation escaping the hole closely matched that of an ideal blackbody. Experiments with these cavities produced remarkably consistent results. At each temperature, the radiation emitted followed a precise curve. At low frequencies, the emitted energy was modest. It rose to a peak at a particular wavelength, then fell sharply at higher frequencies. This pattern was not random. It was reproducible, precise, and stubbornly consistent across all materials. Nature was offering a clear answer. The challenge was that theory could not follow. Classical physics approached the problem with confidence. Using well-established principles, physicists attempted to calculate how electromagnetic waves behave inside the cavity. The walls of the cavity were thought to contain oscillating charges that emitted radiation. These oscillations could exist at many different frequencies, forming standing waves inside the cavity. By applying classical statistical mechanics, physicists assumed that each mode of vibration should carry the same average amount of energy, according to the principle of energy equipartition. At first, the results seemed promising. The calculations matched experimental data at low frequencies. This agreement reassured scientists that they were on the right path. But as they extended their calculations to higher frequencies, the equations began to misbehave. The predicted energy did not level off or decrease. It rose. And then it rose faster. And then it diverged completely. According to classical theory, the amount of energy emitted at higher and higher frequencies should increase without limit. The total energy emitted by a blackbody, when summed over all frequencies, became infinite. This was not a minor discrepancy. It was a catastrophic failure. An infinite amount of energy being emitted by a finite object at a finite temperature was physically impossible. No experiment showed anything remotely like this. The real world remained calm and finite, while the mathematics exploded into absurdity. This failure became known as the Ultraviolet Catastrophe. The name captured both the region of the spectrum, where the divergence became severe, and the intellectual disaster it represented. The catastrophe was not that ultraviolet light was dangerous, but that classical physics predicted a universe that could not exist. If the equations were correct, every warm object would radiate infinite energy. Matter itself would be unstable. The universe would be flooded with high-frequency radiation. Clearly, this was not happening. Physicists faced an uncomfortable truth. Their theories worked extraordinarily well in many domains, yet here they failed completely. The more carefully they applied classical reasoning, the worse the predictions became. The problem could not be fixed by tweaking constants or improving measurements. The experimental data were solid. The mathematics was consistent. The error lay deeper in the assumptions about how nature handles energy. At the heart of the problem was a belief, so ingrained that it had never been seriously questioned, the idea that energy is continuous. Classical physics treated energy like a fluid that could be divided endlessly into smaller and smaller amounts. An oscillator could possess any value of energy, no matter how tiny. There was no minimum unit, no indivisible portion. This assumption worked beautifully for macroscopic systems and had never caused trouble before. But inside the blackbody cavity, it led to an infinite number of high-frequency modes, each contributing energy without limit. The crisis was not just technical, it was philosophical. It forced physicists to confront the possibility that their most basic intuitions about nature were wrong. The smooth, continuous picture of reality, inherited from centuries of classical thought, might not apply at the microscopic level. The glow of heated matter was revealing something profoundly unsettling. Nature might operate in steps rather than flows. What made the situation even more disturbing was that no one initially knew how to fix it. Different formulas were proposed, some fitting parts of the curve but failing elsewhere. These were empirical patches rather than true explanations. They worked mathematically but offered no insight into why nature behaved this way. The community was divided between those who believed a clever classical solution must exist and those who suspected that something fundamentally new was required. The crisis lingered because it struck at the limits of human understanding. Classical physics had succeeded by reducing complex phenomena to simple principles. Now those principles themselves were under suspicion. The blackbody problem was not asking for a better equation, it was asking a deeper question about the nature of energy, matter, and light. This moment in history marks a turning point. The confidence of classical physics, built over centuries, encountered a phenomenon it could not tame. The failure was not gradual or subtle, it was absolute. The equations predicted infinities where none existed. Theories that had once felt universal suddenly appeared fragile. The Blackbody Radiation Crisis revealed that even the most successful scientific frameworks have boundaries. It demonstrated that experimental facts are the ultimate judges of theory, not mathematical elegance or philosophical comfort. Most importantly, it prepared the stage for a radical transformation in physics, one that would redefine how humanity understands reality at its most fundamental level. This problem, born from something as simple as a glowing object, showed that nature does not always conform to human expectations. It hinted that beneath the smooth surface of classical laws lies a deeper structure, one governed by rules that would soon overturn centuries of certainty. As the implications of this failure became impossible to ignore, the scientific world entered a period of quiet tension. There was no dramatic announcement that classical physics was broken, no single moment of collapse. Instead, there was a growing unease, a recognition that something essential was missing. The blackbody radiation problem refused to go away. It reappeared in laboratories across Europe, in calculations repeated by different minds, and in discussions that stretched late into the night among physicists who sensed they were standing at the edge of an intellectual cliff. What made the situation so troubling was not only that classical physics failed, but that it failed in such a stark and uncompromising way. Other scientific errors in the past had been corrected by refining assumptions or extending existing theories. This was different. The predictions did not merely disagree with experiment, they diverged into nonsense. Infinity appeared where finiteness was required. And infinity in physics is not just a large number, It is a sign that a theory has lost contact with reality. The deeper physicists looked, the clearer it became that the problem could not be blamed on experimental imperfections. The measurements of blackbody radiation were among the most precise of the era. Different materials, different cavity shapes, different experimental setups all produced the same curves. Nature was speaking with a single voice. The problem lay entirely on the theoretical side. At the center of this crisis was the relationship between matter and radiation. Classical physics treated light as a wave and matter as a continuous medium filled with oscillators that could vibrate at any frequency. Inside a blackbody cavity, these oscillators were assumed to exchange energy freely with the electromagnetic field. The mathematics that described this exchange was elegant and internally consistent. And yet, when pushed to its logical conclusion, it led straight to catastrophe. This exposed a dangerous assumption, that the microscopic world behaves like a scaled-down version of the macroscopic one. Classical physics assumed that the same rules governing visible objects applied without modification to atoms and electrons. The blackbody problem shattered this assumption. It suggested that the microscopic realm might obey rules that have no counterpart in everyday experience. Some physicists resisted this implication. They believed that a clever reinterpretation of classical ideas would eventually resolve the issue. Others began to suspect that the crisis was signaling the need for a conceptual leap, something as radical as the abandonment of continuity itself. But at the time, this idea was almost unthinkable. Continuity was not just a mathematical convenience, it was woven into the philosophical fabric of physics. The discomfort was intensified by the fact that the blackbody problem sat at the intersection of multiple disciplines. It involved thermodynamics, electromagnetism, and statistical mechanics, all of which were considered mature and reliable theories. To accept that the problem required a fundamentally new approach meant accepting that the foundations of physics were incomplete. This was not an easy admission for a field that had enjoyed decades of triumph. As debates continued, the crisis quietly reshaped how physicists thought about explanation itself. It became clear that mathematical success alone was not enough. A theory could match data and still be conceptually wrong. Conversely, a theory could be logically beautiful and still fail in the face of experiment. The blackbody radiation crisis forced physicists to confront the limits of purely classical reasoning. There was also a psychological dimension to the crisis. Many physicists had built their careers on classical ideas. To accept that these ideas were fundamentally flawed at a deep level was to accept that decades of work rested on incomplete foundations. This created a natural resistance to radical change, yet nature did not negotiate. The data remained unchanged, indifferent to human reluctance. What the crisis truly revealed was that energy itself had been misunderstood. Classical physics treated energy as an abstract bookkeeping quantity, something that could be redistributed endlessly, without restriction. But the behavior of blackbody radiation suggested that energy might have a structure of its own, governed by rules that limit how it can be exchanged. This idea was both unsettling and profound. The glow of heated matter thus became more than a technical puzzle. It became a message from nature, a signal that the universe does not operate according to human intuition alone. It showed that the assumptions inherited from centuries of observation at human scales break down when applied to the microscopic world. The crisis was not about light alone, it was about the nature of physical law. In retrospect, what makes the blackbody radiation crisis so important is not just that it exposed a flaw in classical physics, but that it demonstrated how scientific progress actually occurs. It did not arise from speculative philosophy or abstract mathematics. It arose from careful measurement, from the refusal to ignore inconvenient facts, and from the willingness to accept that even the most trusted theories can fail. The crisis also marked a shift in the role of experiments. Experiments were no longer merely tests of theory, they became guides pointing toward entirely new ways of thinking. The blackbody curve did not suggest a minor correction. It demanded a new conceptual framework. It was nature's way of saying that the old language of physics was no longer sufficient. This realization prepared the scientific community, slowly and painfully, for a revolution. Even before a solution emerged, the crisis had already done its work. It had broken the illusion of completeness. It had shown that classical physics, for all its power, was not the final word on reality. It had created a space where new ideas could take root. The Blackbody Radiation Crisis stands as a reminder that scientific certainty is always provisional. Theories are tools, not truths etched into the fabric of existence. When those tools fail, the failure is not a disaster but an opportunity. It is through such failures that deeper understanding becomes possible. In the end, the most important legacy of this crisis is not the equations it invalidated, but the humility it imposed. It taught physicists that nature does not owe us simplicity, continuity, or comfort. It operates according to its own rules, and our task is not to impose our expectations upon it, but to listen carefully when it reveals its secrets. What began as an attempt to explain why objects glow when heated became a turning point in human knowledge. The inability of classical physics to solve this problem was not a dead end, but a doorway. Beyond it lay a new vision of reality, one that would transform science, technology, and our understanding of the universe itself. When physicists first spoke about blackbody radiation, they were not trying to describe something exotic or mysterious. They were trying to understand one of the most common experiences in nature, the way objects emit light and heat when their temperature changes. Long before equations entered the picture, humans had observed this phenomenon intuitively. Fire glows red and orange, metal turns white, hot in a forge, stars shine with different colors depending on their temperature. What scientists sought was not poetry, but precision. They wanted to know exactly how and why matter emits radiation, and whether this behavior follows universal rules. At the center of this investigation is the concept of radiation itself. Radiation is energy traveling through space in the form of electromagnetic waves. These waves span a vast spectrum, from radio waves to microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The only difference between these forms is their wavelength and frequency. To the human eye, only a tiny slice of this spectrum is visible, but nature operates across all of it at once. Any object with a temperature above absolute zero emits electromagnetic radiation. This is not a special property of flames or stars, it is a fundamental consequence of thermal motion. Inside any material, atoms and molecules are constantly vibrating. As they move, charged particles accelerate, and accelerating charges emit electromagnetic waves. The hotter the object, the more intense this motion becomes, and the more radiation is emitted. What makes blackbody radiation special is not that it emits radiation, but how it emits it. A blackbody is an idealized object that absorbs all incoming radiation and reflects none. It does not matter what the radiation's wavelength is or where it comes from, the blackbody absorbs it completely. Because of this perfect absorption, the radiation it emits depends only on its temperature, not on its composition, shape, or surface properties. This makes blackbody radiation a universal phenomenon governed by temperature alone. In practice, physicists approximated blackbodies using cavities. Imagine a hollow box with perfectly absorbing walls and a tiny hole on one side. Radiation entering the hole becomes trapped inside, bouncing back and forth, gradually being absorbed by the walls. The radiation inside the cavity reaches thermal equilibrium with the walls. The small amount of radiation that escapes through the hole is an almost perfect representation of blackbody radiation. This clever setup allowed scientists to study the phenomenon under controlled conditions. When measurements were taken, a remarkable pattern emerged. For a given temperature, the intensity of emitted radiation varied with wavelength in a very specific way. At long wavelengths, corresponding to low frequencies, the emitted energy was relatively small. As the wavelength shortened, the intensity increased, reaching a maximum at a particular wavelength. Beyond this peak, the intensity dropped sharply as wavelengths became even shorter. This curve was smooth, continuous, and highly reproducible. As the temperature increased, two things happened. First, the total amount of radiation emitted increased. Hotter objects radiate more energy overall. Second, the peak of the curve shifted toward shorter wavelengths. This explains why cooler objects glow red while hotter ones glow white or blue. The color of an object is directly linked to the wavelength at which its emission is strongest. This relationship between temperature and peak wavelength was later formalized into a precise law, but its empirical truth was clear long before it was fully understood. What made blackbody radiation so powerful as a scientific concept was its universality. It did not matter whether the cavity walls were made of iron, ceramic, or carbon. It did not matter whether the shape was spherical or rectangular. As long as thermal equilibrium was achieved, the emitted radiation followed the same curve. This suggested that blackbody radiation was revealing something fundamental about nature itself, not about specific materials. For classical physics, this seemed like an ideal problem. Electromagnetic theory, developed by Maxwell, had already unified electricity, magnetism, and light. Statistical mechanics had provided tools for connecting microscopic motion with macroscopic properties like temperature and pressure. Thermodynamics described the flow of energy and the concept of equilibrium. Blackbody radiation sat precisely at the intersection of these powerful theories. Inside the cavity, electromagnetic waves form standing wave patterns determined by the size and shape of the cavity. Each possible standing wave corresponds to a mode of vibration, a way the electromagnetic field can oscillate. Classical physics assumed that these modes were like tiny harmonic oscillators, each capable of storing and exchanging energy with the cavity walls. According to classical statistical mechanics, energy should be distributed evenly among all available modes of motion at thermal equilibrium. This principle, known as equipartition, had been extraordinarily successful in explaining the behavior of gases and solids. Each mode was expected to carry an average energy proportional to temperature. There was no reason, within classical thinking, to treat high-frequency modes differently from low-frequency ones. This is where the elegance of the idea met its hidden danger. The number of possible modes inside a cavity increases rapidly as the frequency increases. There are far more ways for high-frequency waves to exist than low-frequency ones. If each mode carries the same average energy, then the total energy at high frequencies should be enormous. At low frequencies, this reasoning worked beautifully. The predicted radiation intensity matched experimental data almost perfectly. This success reinforced confidence in the classical approach, but as measurements extended into shorter wavelengths, the predictions and reality began to part ways. The experiments showed that high-frequency radiation was suppressed. The intensity dropped off sharply beyond the peak. Classical theory, however, insisted that it should continue rising. This divergence was not subtle. It grew worse with each increase in frequency. Eventually, the theory predicted infinite energy, while experiments showed almost none. Understanding what blackbody radiation is, therefore, requires recognizing that it is not merely radiation emitted by hot objects, but radiation governed by a precise and universal distribution. It is a fingerprint of thermal equilibrium between matter and electromagnetic fields. This fingerprint encodes deep information about how energy is stored, transferred, and limited at the microscopic level. The importance of blackbody radiation extends far beyond laboratory cavities. Stars are nearly perfect blackbodies. The color and intensity of starlight reveal their surface temperatures. The cosmic microwave background radiation, the faint afterglow of the early universe, follows an almost perfect blackbody spectrum, providing strong evidence for the Big Bang model. Even modern technologies, from infrared cameras to thermal sensors, rely on principles derived from blackbody radiation. Yet in the late 19th century, none of these broader implications were fully visible. Physicists were focused on a simpler goal: to explain the curve. What they did not yet realize was that this curve was exposing a fundamental mismatch between classical ideas and physical reality. Blackbody radiation is, at its core, a conversation between matter and light. It is the way energy equilibrates between vibrating atoms and electromagnetic fields. The fact that this conversation follows strict rules, independent of material details, tells us that these rules arise from nature's deepest structure. The failure to explain blackbody radiation was not due to a lack of experimental skill or mathematical sophistication. It was due to an incorrect assumption about how energy behaves. The phenomenon itself was simple, elegant, and universal. The theories used to describe it were powerful, but incomplete. To understand blackbody radiation, then, is to understand why classical physics was challenged. It reveals how something seemingly ordinary can expose extraordinary truths. The glow of a heated object is not just a visual effect, it is a window into the microscopic rules governing the universe. This realization did not arrive all at once. It emerged gradually, through careful measurement, repeated failure, and growing unease. But once understood, blackbody radiation became one of the most important phenomena in the history of physics. It was the bridge between the classical world and the quantum one, even before anyone knew that such a bridge existed. In observing how objects radiate energy purely as a function of temperature, physicists stumbled upon a universal law of nature that classical thinking could not contain. Blackbody radiation is therefore not just a definition or a curve on a graph. It is a revelation that the universe, at its most fundamental level, behaves in ways that defy our everyday intuition and demand entirely new ways of thinking. As understanding deepened, physicists began to realize that blackbody radiation was not simply another thermal effect to be cataloged and moved past. It was a diagnostic tool, a kind of mirror reflecting the true nature of how energy behaves when matter and light interact at equilibrium. The more carefully the phenomenon was examined, the more it became clear that blackbody radiation was exposing rules that applied everywhere, not just inside laboratory cavities. One of the most striking realizations was that blackbody radiation is entirely democratic. It does not care about chemical composition, atomic structure, or surface texture. A cavity made of iron behaves the same as one made of ceramic or carbon once equilibrium is reached. This universality was deeply unsettling and deeply powerful at the same time. It meant that the radiation curve was not telling a story about matter, but about energy itself. This shifted the way physicists framed the question. Instead of asking how specific materials emit light, they began asking how energy distributes itself among electromagnetic waves in thermal equilibrium. The cavity walls became secondary. The real system of interest was the electromagnetic field trapped inside the cavity, exchanging energy with matter until balance was achieved. In this equilibrium, radiation is constantly being emitted and absorbed. The cavity walls emit radiation due to thermal motion, while simultaneously absorbing radiation from the field. The observed spectrum is the result of a perfect balance between these processes. This balance is delicate and exact. Any small deviation would immediately shift the spectrum, yet experiments showed extraordinary stability. Nature was enforcing a precise rule. The role of temperature became central. Temperature was no longer just a measure of how hot something felt. It became a controlling parameter that determined the entire shape of the radiation spectrum. Increase the temperature, and the curve rises and shifts. Decrease it, and the curve falls and moves toward longer wavelengths. This intimate link between temperature and radiation hinted that thermal energy and electromagnetic energy were more deeply connected than previously thought. At long wavelengths, corresponding to low frequencies, blackbody radiation behaves in a way that classical physics could explain. This region follows expectations derived from wave theory and thermodynamics. The success in this domain was not accidental. It reflected the fact that at low frequencies, energy exchanges are large compared to whatever microscopic constraints might exist. Classical approximations work when quantum effects are negligible, even if no one yet used that language. But as attention moved toward shorter wavelengths, the behavior changed dramatically. High-frequency radiation did not grow arbitrarily strong. Instead, it was sharply suppressed. This suppression was not gradual or ambiguous, it was decisive. Nature was enforcing a limit, cutting off the contribution of high-frequency modes in a way that classical theory could not justify. This raised an uncomfortable question. Why should high-frequency electromagnetic waves be treated differently from low-frequency ones? Classical physics offered no mechanism for discrimination. A wave was a wave. Frequency changed the oscillation rate, but not the fundamental rules governing energy exchange. And yet, blackbody radiation was telling a different story. The problem lay not in the waves themselves, but in how energy was being shared. Classical theory assumed that every possible mode of vibration could be excited freely, each receiving its fair share of energy. Blackbody radiation revealed that this assumption was false. Some modes were effectively inaccessible, not because they did not exist, but because energy could not flow into them under ordinary thermal conditions. This insight transformed the interpretation of the radiation curve. The curve was not simply showing how much radiation was emitted at different wavelengths. It was showing which energy states were allowed and which were suppressed. In other words, it was a map of accessibility in energy space. Although physicists did not yet have the language to describe this in terms of discrete energy levels, the implication was already present. The cavity contained an infinite number of possible modes, but only a finite subset actively participated in thermal equilibrium. The rest were effectively silent. This realization forced a re-evaluation of how equilibrium itself was understood. Classical equilibrium assumed that given enough time, all degrees of freedom would be equally populated according to temperature. Blackbody radiation showed that equilibrium could exist even when large classes of degrees of freedom were excluded. This was a radical departure from classical statistical thinking. The phenomenon also blurred the distinction between matter and radiation. In classical physics, matter and light were treated as separate entities, interacting but fundamentally different. Blackbody radiation showed that in thermal equilibrium, this distinction becomes secondary. Energy flows seamlessly between vibrating atoms and electromagnetic fields, and the resulting distribution cannot be attributed to one or the other alone. This had profound implications for astrophysics and cosmology, even before those fields fully realized it. Stars, which behave approximately as blackbodies, could now be studied as thermal radiators whose spectra directly reveal their temperatures. The color of starlight became a quantitative diagnostic tool rather than a qualitative observation. The universe itself began to look like a thermodynamic system governed by radiation laws. Blackbody radiation also forced physicists to confront the limits of visualization. Classical physics relied heavily on mechanical analogies, oscillators, waves, particles bouncing like billiard balls. The radiation curve resisted such imagery. There was no classical picture that could explain why high-frequency modes were suppressed while low-frequency ones flourished. The behavior was mathematical and statistical, not mechanical. As experimental precision improved, the agreement between measurements and the observed curve became even more striking. The peak position, the overall shape, the rapid decline at short wavelengths, all were confirmed repeatedly. This left no room for doubt. Blackbody radiation was not an approximation or a special case, it was a fundamental feature of nature. What made this especially significant was that blackbody radiation was unavoidable. Any object at a non-zero temperature emits it. This meant that the phenomenon was not confined to exotic laboratory conditions. It was everywhere. The walls of a room, the surface of the Earth, the background glow of the cosmos, all participate in this universal radiation process. The more physicists reflected on this, the clearer it became that understanding blackbody radiation was equivalent to understanding how nature limits itself. The suppression of high-frequency radiation was not an accident, it was a rule. And rules of this kind usually signaled deep principles at work. This led to a subtle but crucial shift in mindset. Instead of asking how classical theory could be fixed to accommodate blackbody radiation, physicists began asking what blackbody radiation was trying to teach them. The curve was no longer a problem to be solved, it was a clue to a deeper structure. In hindsight, blackbody radiation can be seen as nature's way of introducing a new idea gently, without explanation. It presented the result without revealing the mechanism. The curve was the answer, but the question had not yet been properly formulated. By studying what blackbody radiation is, physicists were unknowingly studying the boundaries of classical thought. They were discovering that energy, frequency, and temperature are linked in ways that defy continuous assumptions. The phenomenon stood as a silent challenge, daring theory to catch up with reality. This is why blackbody radiation occupies such a central place in the history of physics. It is not merely a definition or a model. It is a universal behavior that exposes the limitations of old ideas and points toward new ones. It shows that even the simplest observations, when examined with enough care, can overturn entire worldviews. The glow of heated matter, once taken for granted, became a messenger of revolution. Without drama, without intention, it revealed that nature organizes energy according to rules deeper than classical physics could imagine. And in doing so, it prepared the ground for a new understanding of the universe, one in which limits, discreteness, and structure replace continuity and excess. Blackbody radiation is therefore not just something that happens when objects get hot. It is a statement about how the universe distributes energy, about what is allowed and what is forbidden, about how equilibrium is achieved not through unlimited sharing, but through subtle constraint. Long before the word quantum entered the scientific vocabulary, blackbody radiation had already begun to define what it would mean. By the end of the 19th century, the confidence of physics rested on a powerful belief that nature, when properly understood, would never lead to absurd results. Equations might be complex, calculations difficult, but reality itself was assumed to be orderly, finite, and sensible. This belief was shattered when scientists followed classical laws to their logical conclusion and encountered one of the most disturbing predictions ever produced by a respected theory. This prediction did not merely contradict experiment, it threatened the very possibility of a stable universe. That moment is what later came to be known as the Ultraviolet Catastrophe. The catastrophe emerged not from careless reasoning, but from rigorous logic applied with discipline. Physicists began by modeling the electromagnetic radiation inside a heated cavity. Inside this enclosed space, light behaves as standing waves, reflecting back and forth between the walls. Each standing wave corresponds to a specific frequency and wavelength, determined by the geometry of the cavity. These waves were treated as independent modes of vibration, much like the harmonics on a stretched string. Classical statistical mechanics provided the next step. According to its principles, when a system reaches thermal equilibrium, energy is distributed equally among all available degrees of freedom. Each mode of vibration should, on average, carry an energy proportional to the temperature of the system. This idea, known as equipartition of energy, had explained countless physical phenomena with remarkable success. There was no reason to doubt it. At low frequencies, this approach worked perfectly. The predicted intensity of radiation matched experimental measurements. This agreement reinforced confidence that the method was sound. But as physicists extended their calculations to include higher frequencies, something strange began to happen. The number of possible modes increased rapidly. For every increase in frequency, there were more and more ways for electromagnetic waves to fit inside the cavity. Mathematically, this meant that while each mode carried a modest amount of energy, the sheer number of high-frequency modes caused the total energy to explode. The equations showed that as frequency increased, the energy density of radiation increased without bound. There was no peak, no decline, no suppression. The curve simply rose forever. This was the ultraviolet catastrophe. According to classical theory, most of the energy emitted by a hot object should be concentrated at extremely high frequencies, far beyond visible light, deep into the ultraviolet and beyond. Worse still, when all frequencies were included, the total emitted energy became infinite. This result was not just incorrect, it was nonsensical. An infinite amount of energy cannot be emitted by an object with finite temperature and finite size. If classical physics were right, even mildly warm objects would radiate infinite energy, draining themselves instantly and flooding the universe with high-frequency radiation. The fact that this clearly did not happen meant that something was fundamentally wrong. What made the ultraviolet catastrophe so shocking was that it arose from the most trusted theories of the time. Maxwell's equations for electromagnetism were considered nearly perfect. Statistical mechanics had proven its power across thermodynamics. The catastrophe did not come from fringe ideas or speculative assumptions. It emerged from the very heart of classical physics. Physicists were forced to confront a brutal truth. Their equations were predicting a universe that could not exist. This was not a small mismatch between theory and experiment that could be blamed on measurement error. The discrepancy grew larger the more carefully the theory was applied. Precision made the failure worse, not better. The ultraviolet catastrophe revealed a deep misunderstanding about how nature handles high-frequency energy. Classical physics assumed that nothing prevented energy from flowing into arbitrarily small wavelengths. There was no mechanism to limit excitation at high frequencies. The theory treated all modes equally, regardless of how rapidly they oscillated, but nature clearly did not. Experiments showed that high-frequency radiation was suppressed. Instead of rising endlessly, the radiation curve peaked and then dropped off sharply. This suppression was not gradual or subtle. It was decisive. The universe itself was enforcing a cutoff. The catastrophe, therefore, was not merely about ultraviolet light. It was about the failure of continuity. Classical physics assumed that energy could be divided endlessly, shared freely, and distributed smoothly across all possible modes. The infinite result was the natural consequence of this assumption. The fact that reality avoided this infinity suggested that the assumption itself was wrong. This realization struck at the philosophical core of classical science. For centuries, continuity had been a guiding principle. Motion was continuous, forces acted smoothly, energy flowed without jumps. To abandon continuity was to abandon a worldview inherited from Newton and refined over generations. Yet the ultraviolet catastrophe left no alternative. Either classical physics was incomplete, or the universe was impossible. Since the universe clearly existed, the conclusion was unavoidable. The name, ultraviolet catastrophe, captures the drama of the situation. But the true catastrophe was intellectual. It marked the moment when physicists realized that their understanding of nature had reached a breaking point. Theories that worked beautifully at large scales failed catastrophically at small ones. This failure was deeply unsettling because it could not be isolated. If classical physics failed here, where else might it fail? The blackbody problem was not a niche phenomenon. Every object emits radiation. The catastrophe implied that classical physics was wrong everywhere, not just in specialized conditions. The reaction among physicists was mixed. Some hoped that a clever mathematical correction could save classical ideas. Others suspected that an entirely new framework was needed. But even those who sensed a revolution coming could not yet imagine its form. The ultraviolet catastrophe also revealed a crucial lesson about infinity in physics. Whenever a theory predicts infinite measurable quantities, it signals that the theory has been pushed beyond its domain of validity. Infinity is not a physical result, it is a warning sign. In this case, the warning was loud and unmistakable. What made this moment historic was not simply that a problem existed, but that it could not be ignored. The blackbody radiation curve was too precise, too universal, too well measured. Nature was not ambiguous. The failure of theory was complete. The catastrophe thus became a turning point. It showed that classical reasoning, no matter how sophisticated, was insufficient to describe the microscopic world. It forced physicists to consider the possibility that energy exchange itself might be restricted, governed by rules that classical physics did not recognize. This was an extraordinary idea for its time. To suggest that nature imposes limits on energy distribution was to suggest that there are forbidden processes, inaccessible states, and built-in constraints at the deepest level of reality. The ultraviolet catastrophe, then, was not simply an embarrassment for classical physics. It was a revelation. It exposed the assumptions that had gone unquestioned for centuries and demonstrated that they could no longer be maintained. By predicting infinite energy where none existed, classical physics revealed its own boundaries. The catastrophe was the moment when the old framework reached its breaking point, when the smooth, continuous picture of the universe fractured under the weight of experimental truth. In hindsight, this failure was not the end of physics, but the beginning of a deeper one. The ultraviolet catastrophe did not destroy science, it redirected it. It showed that to understand nature, physicists would have to let go of comforting assumptions and accept that reality operates according to rules far stranger and far more constrained than classical intuition had ever allowed. As the shock of this realization settled in, physicists began to understand that the ultraviolet catastrophe was not an isolated mathematical oddity, but a symptom of a much deeper problem. It was evidence that the classical description of nature, however successful at everyday scales, was being pushed beyond its legitimate limits. The catastrophe did not arise from sloppy reasoning or missing terms, it emerged precisely because the reasoning was consistent. This made it impossible to dismiss. What disturbed scientists most was how unavoidable the conclusion seemed. If one accepted the core assumptions of classical physics, the catastrophe followed inevitably. There was no hidden switch that could be flipped, no parameter that could be adjusted to restore sanity. The mathematics marched relentlessly toward infinity. The more faithfully physicists followed classical logic, the more violently it clashed with reality. This forced a painful reassessment of what it meant for a theory to be true. Classical physics was not wrong in the sense that it failed everywhere. It still explained planetary motion, sound waves, electrical circuits, and countless other phenomena with astonishing accuracy. But the ultraviolet catastrophe revealed that truth in physics is conditional. A theory can be extraordinarily accurate within a certain domain, and yet fundamentally incomplete outside it. The catastrophe also highlighted a critical distinction between mathematical possibility and physical reality. Classical equations allowed energy to be distributed among infinitely many modes, but nature clearly refused to do so. This meant that not everything that mathematics permits actually occurs in the physical world. There are constraints embedded in reality that mathematics alone does not reveal unless guided by experiment. As discussions deepened, physicists began to recognize that the real issue was not light, not heat, and not even radiation, but the way energy itself behaves at small scales. The assumption that energy could be divided without limit had never been experimentally tested in the microscopic domain. It had simply been assumed, because it worked so well elsewhere. The ultraviolet catastrophe was the first clear signal that this assumption might be false. This realization marked a subtle shift in scientific humility. For generations, physicists had believed that the laws governing the macroscopic world could be smoothly extended downward to explain atoms and molecules. The catastrophe showed that nature does not always cooperate with extrapolation. The microscopic world has its own rules, and they cannot be guessed purely from large-scale behavior. The ultraviolet catastrophe also reshaped how physicists viewed failure. Instead of seeing the breakdown of classical theory as an embarrassment, some began to see it as an opportunity. Failures of this magnitude are rare, and when they occur, they often signal the presence of something profoundly new. The catastrophe was not a dead end, it was a signpost. This period of uncertainty created a fertile intellectual environment. Physicists became more open to unconventional ideas, more willing to question assumptions that had once seemed untouchable. Concepts that would have been dismissed as absurd a decade earlier began to receive cautious attention. The rigidity of classical thinking started to soften. Importantly, the catastrophe also taught physicists how to interpret infinity. In classical mathematics, infinity can be a valid and even useful concept. In physics, however, infinity almost always indicates that a theory has been applied beyond its scope. The ultraviolet catastrophe became one of the clearest examples of this principle. It demonstrated that when equations predict infinite measurable quantities, the problem lies not with nature, but with the assumptions behind the equations. The intellectual impact of this lesson extended far beyond blackbody radiation. It influenced how future theories were constructed and tested. Physicists became more cautious about assuming continuity, smoothness, and unlimited divisibility. They learned to treat such assumptions as hypotheses rather than truths. Another profound consequence was the erosion of determinism at the microscopic level. Classical physics had offered a universe governed by precise, predictable laws. The ultraviolet catastrophe hinted that at small scales, predictability might be limited by fundamental constraints. This idea was unsettling, but it opened the door to a richer and more accurate description of reality. As the crisis matured, it became clear that the ultraviolet catastrophe was not something that could be patched over. It demanded a conceptual breakthrough, not a technical fix. The solution would require rethinking what energy is, how it is exchanged, and what limits nature imposes on physical processes. In hindsight, the catastrophe can be seen as nature's way of forcing a pause. It stopped physics in its tracks and demanded attention. It reminded scientists that no matter how successful a theory may be, it is always provisional. Reality is the final authority, and when it disagrees with theory, theory must change. The ultraviolet catastrophe also demonstrated the power of simple phenomena to reveal deep truths. The glow of a heated object, something observed since the dawn of humanity, turned out to contain within it the seeds of a revolution. This underscores a central lesson of science. Profound discoveries often emerge not from exotic experiments, but from careful attention to ordinary facts. By confronting physicists with an impossible prediction, the catastrophe made it clear that the classical worldview had reached its limit. It did not invalidate everything that came before, but it showed that the story was incomplete. A new chapter was required, written in a language that classical physics did not possess. This realization prepared the ground for one of the most dramatic transformations in the history of science. The ultraviolet catastrophe did not itself provide the solution, but it made the need for a solution undeniable. It stripped away complacency and forced the scientific community to accept that the universe is governed by deeper, subtler rules than those revealed by classical thought. In this sense, the catastrophe was not a failure of science, but a triumph of it. Science worked exactly as it should. Experiment exposed the limits of theory, and those limits pointed the way forward. The ultraviolet catastrophe stands as a reminder that when nature refuses to obey our expectations, it is not nature that is wrong. It is our understanding that must evolve. The prediction of infinite energy was not an accident of sloppy mathematics or a misunderstanding of experimental data. It arose naturally and unavoidably from the core principles of classical physics. To understand why classical laws produced such impossible results, it is necessary to look closely at the assumptions hidden inside those laws, assumptions that had worked so well for centuries that no one thought to question them. At the heart of classical physics was the idea of continuity. Energy was assumed to be infinitely divisible. There was no smallest unit, no lower limit to how little energy a system could possess or exchange. An object could absorb or emit energy in arbitrarily small amounts, smoothly and continuously, just like water flowing through a pipe. This assumption felt self-evident because it matched everyday experience. When we heat something, it warms gradually. When we dim a light, its brightness fades smoothly. Nothing in daily life suggests that energy comes in chunks. This idea of continuity was deeply embedded in classical mechanics, thermodynamics, and electromagnetism. When physicists applied these laws to blackbody radiation, they treated the electromagnetic field inside a cavity as a collection of standing waves, each one a possible mode of vibration. Importantly, classical theory allowed an unlimited number of these modes, especially at very high frequencies. There was no built-in restriction preventing waves from oscillating faster and faster. Classical statistical mechanics then entered the picture with another powerful assumption, the principle of equipartition of energy. According to this principle, every independent mode of motion in a system at thermal equilibrium should, on average, carry the same amount of energy, proportional to temperature. This idea had been extraordinarily successful in explaining gases, heat capacity, and mechanical systems. There was no reason, within classical thinking, to doubt it. When equipartition was applied to blackbody radiation, each electromagnetic mode inside the cavity was treated like a tiny harmonic oscillator. Each one was assigned the same average energy. On its own, this was not problematic. The trouble came from combining this assumption with the fact that the number of available modes increases rapidly with frequency. As frequency increases, the wavelengths become shorter, and more standing waves can fit inside the cavity. Mathematically, the number of modes grows roughly with the square of the frequency. This means that at high frequencies, there are vastly more modes than at low ones. If each mode carries the same average energy, then the total energy at high frequencies becomes enormous. Classical physics had no mechanism to stop this growth. There was nothing in Maxwell's equations that limited how fast electromagnetic waves could oscillate. There was nothing in thermodynamics that restricted how energy should be shared among modes. The result was inevitable as frequency increased. The predicted energy density increased without bound. This is why infinity appeared. It was not introduced artificially. It emerged because classical physics treated all frequencies as equally accessible and all modes as equally likely to be excited. The mathematics faithfully followed these assumptions and delivered their logical conclusion. The catastrophe was the theory being consistent with itself, but inconsistent with reality. The reason this result was so shocking is that classical physics had always relied on smooth averages. It worked brilliantly when dealing with large numbers of particles and long timescales. In those regimes, individual microscopic details wash out, and continuity becomes a good approximation. But blackbody radiation exposed a situation where microscopic behavior mattered critically, and classical averaging failed. Another key issue was that classical physics assumed there was no cost associated with accessing higher frequencies beyond the energy itself. In reality, high-frequency oscillations require very specific conditions. But classical theory treated them as just another option, no different in principle from low-frequency ones. This assumption dramatically overestimated how much energy could flow into those modes. The infinite result was therefore a sign that classical physics was overcounting possibilities. It assumed that nature would populate every mathematically allowed mode, even when doing so would require absurd amounts of energy. Reality clearly refused to cooperate. What classical laws were missing was a constraint, a rule that limits how energy can be distributed at small scales. Without such a rule, the mathematics runs wild. Infinity becomes unavoidable. The failure was not that classical equations were wrong in form, but that they were missing a crucial piece of physical truth. This is why the ultraviolet catastrophe could not be fixed by adjusting constants or improving measurements. The problem was structural. As long as energy was treated as continuous and equipartition was assumed to hold at all frequencies, infinity would always appear. The laws themselves demanded it. In this sense, the infinite prediction was a gift disguised as a disaster. It revealed exactly where classical physics broke down. It showed that nature does not allow unlimited access to high-frequency energy states. There are restrictions, boundaries, and thresholds that classical theory could not describe. The impossibility of infinite energy forced physicists to confront the fact that something fundamental was missing from their understanding. It suggested that energy exchange might occur only in specific amounts, or that certain modes might be inaccessible unless special conditions were met. These ideas were radical at the time, But the mathematics left no alternative. Classical laws gave infinite results because they assumed a universe without limits at the microscopic level. Blackbody radiation proved that such a universe does not exist. Nature is constrained, selective, and economical in how it distributes energy. Infinity was the warning sign that classical physics had reached the edge of its domain. The appearance of infinity was not a failure of logic. It was the final, unmistakable signal that a new way of thinking was required. At the turn of the 20th century, the crisis surrounding blackbody radiation reached a point where even the most cautious physicists accepted that something unprecedented was required. The equations of classical physics had been followed faithfully, and they had led to absurdity. Into this moment stepped Max Planck, a man who did not see himself as a revolutionary, but as a conservative physicist trying desperately to preserve order where chaos had appeared. Planck was deeply committed to classical ideas. He believed in determinism, continuity, and the established laws of thermodynamics. When he confronted the blackbody radiation problem, his goal was not to overthrow classical physics, but to find a mathematical expression that fit the experimental data. He was disturbed by the empirical formulas that matched observations without offering physical meaning. To him, a formula without interpretation was incomplete. Working with extreme caution, Planck attempted to derive the blackbody radiation curve from first principles. He focused on the interaction between the electromagnetic field and the oscillators in the cavity walls. Classical approaches failed repeatedly. Each attempt led back to the same divergence at high frequencies. The mathematics would not behave. In an act he later described as one of desperation, Planck made an assumption that violated the deepest instincts of classical physics. He proposed that the oscillators exchanging energy with radiation could not do so continuously. Instead, they could only absorb or emit energy in discrete amounts proportional to the frequency of the radiation. Energy, he suggested, came in packets. This was not a philosophical claim at first. Planck treated it as a mathematical device, a trick to make the equations work. He introduced a new constant of nature, now known as Planck's constant, to quantify the size of these energy packets. With this assumption in place, he recalculated the distribution of energy inside the blackbody cavity. The result was astonishing. The new formula matched experimental data perfectly across all frequencies. The peak appeared exactly where it should. The rapid drop at high frequencies emerged naturally. The ultraviolet catastrophe vanished completely. Infinity was replaced by order. Yet Planck himself was uneasy. He did not immediately believe that energy was truly quantized. He hoped that the assumption would later be justified or replaced by a deeper classical explanation. To him, quantization was a formal hypothesis, not a statement about reality. Nevertheless, the success of the formula could not be denied. What Planck had done, without fully realizing it, was introduce a fundamental limit into physics. By restricting energy exchange to discrete amounts, he prevented the uncontrolled population of high-frequency modes. The infinite sea of possibilities assumed by classical physics was suddenly fenced off. Only certain transitions were allowed, and that limitation changed everything. This idea marked a profound departure from centuries of thinking. For the first time, energy was not treated as a smooth quantity, but as something granular. The implication was subtle, but devastating for classical intuition. If energy is quantized, then the microscopic world cannot be described by continuous variables alone. Planck's solution worked because it imposed a natural suppression of high-frequency radiation. At ordinary temperatures, the energy required to excite very high-frequency modes became prohibitively large. As a result, those modes remained mostly unoccupied. The radiation spectrum naturally peaked and then declined, exactly as experiments showed. What makes this moment extraordinary is that Planck did not set out to create a new physics. He was attempting to rescue the old one, but in doing so, he crossed a line that could never be uncrossed. Once the idea of quantization entered physics, it refused to remain a mere mathematical convenience. The introduction of Planck's constant signaled that nature has a built-in scale, a smallest action that cannot be divided further. This constant did not arise from measurement error or material properties. It was universal. It applied everywhere, to all forms of radiation and matter. Planck's reluctant assumption soon began to reveal its true power. Other physicists noticed that the same idea could explain phenomena that had resisted classical explanation for years. What began as a desperate fix for blackbody radiation started to look like a glimpse into the true structure of reality. In hindsight, Planck's contribution represents one of the most important turning points in science. He showed that the path forward did not lie in forcing classical ideas to work at all costs, but in accepting that nature operates according to rules that may feel deeply uncomfortable. The radical nature of Planck's solution lies not in its mathematics, but in its implications. It suggests that continuity is an approximation, not a truth. That smoothness emerges only when we average over countless discrete events. At the deepest level, the universe does not flow, it ticks. Planck himself took years to fully accept the meaning of what he had introduced. But history moved faster than his caution. Once the idea existed, it could not be ignored. It reshaped physics from the inside out. The blackbody radiation problem was solved not by refining classical theory, but by transcending it. Planck's solution did more than fix a curve on a graph. It revealed that the universe enforces limits, that it counts energy in units, and that infinity is not allowed. This moment marks the quiet birth of a new worldview, one in which nature is not continuous and unbounded, but structured and constrained. Planck did not announce a revolution. He uncovered it by accident, and in doing so, he changed the course of human understanding forever. The moment energy was understood to be quantized, physics crossed a boundary from which it could never return. What began as a reluctant assumption to fix a mathematical failure quickly revealed itself as a foundational truth about nature. Energy, once imagined as infinitely divisible and smoothly flowing, was now understood to come in discrete units. This single idea did not merely solve one problem, it rewrote the rules of reality. At first, the change seemed narrow in scope. Quantization appeared as a technical detail, relevant only to the interaction between matter and radiation. But as physicists began to explore its consequences, they realized that this idea reached far beyond blackbody radiation. It challenged the very language of classical physics and exposed its limits. One of the first realizations was that quantization introduces thresholds into nature. In a classical world, any process that is allowed can occur gradually, no matter how small the energy involved. In a quantized world, this is no longer true. Certain processes simply cannot happen unless a minimum amount of energy is available. Below that threshold, the process is forbidden. Nature, it seemed, operates with rules of permission and prohibition. This had immediate implications for how matter interacts with light. If energy can only be exchanged in discrete amounts, then atoms cannot absorb or emit arbitrary frequencies of radiation. They must obey strict conditions. This insight soon led to the understanding that atoms possess specific internal energy states. Transitions between these states involve the absorption or emission of precise amounts of energy, no more and no less. This idea shattered classical atomic models. In classical physics, electrons orbiting a nucleus should radiate energy continuously and spiral inward, causing atoms to collapse. Quantization prevented this catastrophe. It explained why atoms are stable and why they emit light at specific frequencies. What had once been an embarrassing contradiction became a triumph of explanation. Quantization also transformed the concept of temperature. Temperature was no longer just a measure of average energy. It became a measure of how many energy quanta are available to populate different states. At low temperatures, only the lowest energy states are accessible. At higher temperatures, more states become available. This view explained why certain physical properties change dramatically with temperature while others remain frozen. The ripple effects continued. The behavior of solids, once explained only approximately, could now be understood in terms of quantized vibrations of atoms in a lattice. heat capacity which classical physics predicted incorrectly at low temperatures, suddenly made sense. Materials stopped absorbing heat not because the equations failed, but because there were no accessible energy states left to occupy. Light itself was reinterpreted. While classical physics described light as a wave, quantization revealed that light also behaves as a collection of discrete packets of energy. This dual character was deeply unsettling. Waves are spread out and continuous. Particles are localized and discrete. Quantization forced physicists to accept that nature does not conform to simple categories. It can be both at once, depending on how it is observed. This shift altered the role of measurement in physics. In a classical world, measurement reveals pre-existing properties. In a quantized world, measurement becomes an active process that selects outcomes from a set of possibilities. Energy does not slide smoothly from one value to another. It jumps, and those jumps cannot be predicted in detail, only in probability. The idea that probability is fundamental, not just a reflection of ignorance, marked a profound departure from classical determinism. Quantization implied that even with perfect knowledge, outcomes could only be predicted statistically. This was not a limitation of technology or mathematics. It was a feature of reality itself. As quantization was applied more broadly, it reshaped every corner of physics. Chemical bonding became understandable as a consequence of quantized electron states. Spectroscopy turned into a precise diagnostic tool, revealing the structure of atoms and molecules. Technologies such as lasers, semiconductors, and magnetic resonance all trace their origins back to the idea that energy is quantized. Even space and time began to be questioned. If energy and action come in discrete units, could other quantities be quantized as well? This question continues to drive modern physics, from attempts to unify quantum theory with gravity to the exploration of the earliest moments of the universe. Perhaps the most profound consequence of quantization is philosophical. It forced humanity to abandon the belief that the universe is ultimately smooth and continuous. Instead, it revealed a world built on limits, thresholds, and indivisible units. Continuity, once seen as fundamental, became an approximation that emerges only at large scales. What makes this transformation remarkable is how quietly it began. There was no dramatic experiment announcing the end of classical physics. There was no sudden collapse of old theories. There was a curve on a graph that refused to behave, and a single assumption that made it behave perfectly. From that assumption flowed a new understanding of reality, one in which nature is not infinitely generous, but carefully structured, one in which not everything that is mathematically conceivable is physically allowed, one in which energy, the most central concept in physics, is counted, not poured. Quantization did not erase classical physics. It explained why classical physics works where it does. At large scales and high energies, the discrete steps blur together, and the world appears smooth. But beneath that smoothness lies a granular structure that governs everything. The change was permanent. Once energy was understood to be quantized, physics gained a new lens through which all phenomena could be viewed. The universe was no longer a continuous symphony, but a composition built from indivisible notes. And from those notes arose the richness, stability, and complexity of the world we observe. This is why quantization did not merely solve a problem, it transformed physics forever. The moment the Blackbody Radiation Crisis was resolved, it became clear that physics had crossed a historical threshold. What began as a technical failure had quietly reshaped humanity's understanding of nature at its deepest level. The crisis did not merely add a new theory to science, it marked the end of an era and the beginning of another. From this point onward, the universe could no longer be described solely by smooth curves, continuous flows, and deterministic certainty. The importance of this moment lies in what it revealed about the limits of classical thinking. Classical physics had succeeded because it mirrored everyday experience. Objects move smoothly, energy seems to flow continuously, and causes appear to lead predictably to effects. These assumptions felt natural, almost inevitable. The blackbody problem showed that these intuitions, while useful, are not universal truths. They are approximations that fail when nature is examined closely enough. By forcing physicists to abandon the idea that energy can be distributed without restriction, the crisis exposed a deeper structure underlying reality. It revealed that nature enforces boundaries. Certain processes are allowed, others are forbidden, not because of external constraints, but because of the internal logic of the universe itself. This realization changed the role of physical laws. They were no longer seen as descriptions of smooth motion alone, but as rules governing what can and cannot happen. This shift had profound consequences for how scientists understood explanation. In classical physics, to explain something meant to trace a continuous chain of causes. In the new framework that emerged, explanation often meant identifying allowed states and forbidden transitions. The focus moved from trajectories to possibilities, from paths to probabilities. This was not merely a technical adjustment, it was a conceptual revolution. The resolution of the blackbody crisis also revealed how scientific revolutions truly occur. There was no dramatic overthrow of classical physics. No one declared it obsolete overnight. Instead, classical physics was shown to be a special case, valid within certain limits but incomplete as a universal description. This subtle reclassification preserved what worked while acknowledging what did not. It demonstrated that progress in science often comes not from destruction, but from refinement and expansion. The birth of quantum theory, which followed directly from this crisis, transformed every field it touched. Atomic physics, chemistry, solid-state physics, and eventually information technology all trace their foundations back to this moment. The devices that define modern life, transistors, lasers, computers, medical imaging, are practical consequences of accepting that energy and matter behave in quantized ways. None of these would exist if classical physics had been sufficient. Beyond technology, the crisis reshaped humanity's relationship with certainty. Classical physics offered a comforting vision of a clockwork universe, predictable and fully knowable in principle. The new view introduced fundamental uncertainty. It taught that even with perfect knowledge, only probabilities can be predicted for certain outcomes. This was not a failure of measurement or intelligence, but a feature of reality itself. This realization was deeply unsettling, but also profoundly liberating. It suggested that the universe is not rigidly predetermined, but structured with flexibility at its core. Outcomes are constrained but not fixed. Nature follows rules, but those rules allow multiple possibilities to coexist until observation forces a choice. This idea continues to challenge intuition, but it has withstood every experimental test. The blackbody radiation crisis also altered how physicists interpret simplicity. Classical physics prized simple, continuous models. Quantum theory revealed that simplicity does not always lie in smoothness. Sometimes it lies in discreteness, in counting rather than flowing, in steps rather than lines. What appears complex at first glance can be governed by remarkably simple underlying principles once the correct framework is adopted. Perhaps most importantly, the crisis demonstrated the power of experimental truth. Elegant equations, long-standing beliefs, and intellectual comfort all yielded to the stubborn facts of observation. The universe did not care that infinity was inconvenient. It simply refused to behave that way. This reinforced a core principle of science: theories serve reality, not the other way around. The glow of heated matter thus became one of the most consequential clues in the history of knowledge. It showed that the universe communicates its deepest secrets through ordinary phenomena, if only we are willing to listen. The crisis was not hidden in distant galaxies or extreme conditions. It was present wherever something was warm. In hindsight, the blackbody radiation crisis stands as the true doorway into modern physics. It marks the point where humanity realized that intuition, shaped by everyday experience, is not sufficient to describe the foundations of existence. It revealed that reality is stranger, more constrained, and more subtle than classical thought had ever imagined. From that moment on, physics was no longer just the study of motion and forces. It became the study of limits, possibilities, and the structure of information itself. The crisis did not merely explain a spectrum of light. It redefined what it means to understand the universe. This is why the Blackbody Radiation Crisis is remembered not as a failure, but as a beginning. It was the moment when nature forced a new language upon science, a language capable of describing a universe built not on continuous certainty, but on quantized structure, probability, and profound order hidden beneath apparent simplicity. What began as a problem of glowing objects became a turning point in human thought. From it emerged a deeper vision of reality, one that continues to shape science, philosophy, and technology to this day.